Welcome back to this course in polymer chemistry, and this will be the last lecture for this course. What we will do in this lecture, we will cover, basically complete our discussion which we are having on chemistry on polymer additives, and we will talk about fire retardants, surface active additives and reinforcing fillers today, and then briefly talk about polymer blends, and then go to the concluding remarks about this course. Let us talk about fire retardant, and we had earlier about 2-3 lectures earlier we discussed the fire retardant the evaluation techniques, how do you measure the fire retardant properties of a polymer sample. For example, that limited oxygen index, we talked about one of the ways to measure the fire retardant properties. The other method we talked about, that UL method, where we burn the sample from a particular distance under particular condition and in presence of some ignitable materials like cotton, and then we range or rank those polymer species depending upon how long they burn and how they burn, and whether they ignite that cotton which is present below the sample. One of the also important thing that about fire retardancy is that whether the polymer during the burning, whether they are generating smoke and toxic gases. So, basically a good fire retardant polymer should not generate lots of smoke, and obviously they should not produce toxic gases. So, fire retardants are chemicals which are used to retard the ignition and burning of plastics by interfering with the chemistry and or the physics of the combustion process. Fire retardant additives enable plastics to meet various fire safety and performance standards imposed upon them. The application of plastics in various common public purpose, like say in aeroplane or in building materials. Now, in those applications, this fire retardancy is a very important criteria for regulatory criteria for the polymers to be used in those applications. Because, for example, if you talk about a building construction material where the polymer used must be a fire retardant, it should not catch or ignite fire easily, or if in case unfortunately it is getting ignited, it should not produce toxic gas or smoke. So, basically this property is required for the applications where it is essential for the polymer to be fire retardant. Now, to design a fire retardant additives, we need to consider the polymer ignitability, the rate of flame spreading, rate of heat release, and formation of smoke and toxic gases, as we mentioned before. One thing one must note, that there is no uniform FR additives. It is not that one FR additive is best for all the polymers. So, it is basically the choice of fire additives depend upon the pair of the polymer and the additives. Basically, one additive may be very good for one polymer, but the same additive may not be as good as for the other polymers. So, it is essential that the combination is chosen rightly. So, no universal FR additives, the performance varies with the final form of product, and generally highly aromatic polymers and the halogen containing polymers are inherently better fire retardant. How the fire retardants work? And they basically prevent this ignition or combustion process by whatever means or some means. For example, they can release the or they can absorb the heat released during the combustion process by releasing water from them. They can form a insulating char on the combustion substrate, and thus by stopping or preventing supply of further fuel to the fire. So, it basically stops the fire and the fire comes down. It can also interfere, you can design additives which interfere with the chemical reactions that maintain the fire. Now, to maintain the fire, they presume that some chemical reactions are happening, which are basically radical processes which maintain and space fire. Now, if we can stop those chemical reaction, then basically we can stop the spreading of the flame. Example. So, this was the basis of choosing or designing fire retardants. Now, we talk about few additives which work by one of these mechanisms. For example, alumina trihydrate, they when in a fire situation, it releases water around 200 degrees centigrade, which basically inhibits the combustion process. So, that is one example of FR additive, one which basically act as fire retardant additives by absorbing heat by releasing water. Second mechanism by which some of the additives may function is by forming insulating char on the substrate, as we just discussed in a minute. And some examples are phosphorus flame retardants, phosphate ester, PVC, and these are used mainly for PVC, polyurethane, polypropylene oxide type polymer. Look at these are mainly inorganic material, because inorganic materials, they do not basically burn in those temperature. Typically organic, you cannot use organic material for char for making insulating char, because organic material themselves burn off. So, mainly phosphorus containing flame retardant act as a flame retardant by forming insulating char. The other flame mechanism by which fire retardant works is by interfering with the chemical reactions that maintain the fire and promotes the spread of the fire. And for example, this halogenated or brominated aromatics, they emits hydrogen bromide during decomposition, and the other halogenated compounds work in that way. They basically trap the radicals, which it is basically assumed or presumed that the radicals which basically spread the fire. So, this HBr or HX halogenated hydrogen halides basically trap those radicals and prevent those chemical reactions which spread fire, and they are mainly used for polymers like nylon, polyester, styrenics and polyolefins. A combination of halogenated FR and antimony trioxides also used some cases, and it is the way it is work that on combustion at a temperature at 600 degree Fahrenheit, these halogens form hydrochloride or hydrobromic acids that reacts with the antimony oxides to form antimony halide or antimony oxyhalides, which basically traps those free radicals and prevent that chemical reactions which basically produces basically it stops or prevents this thermo oxidation processes which generates this volatile or flammable organic compounds, and if they prevents formation of those flammable organic compounds, volatile flammable organic compounds, they basically prevent the burning process. So, this is the mechanism by which halogenated FR along with antimony trioxides synergy works. So, we will talk about next set of additives, which are surface active agents or surface active additives. Now, these additives actually work on different interfaces, for example, polymer air interface or polymer mold interface or interface between two polymeric phases in a blend, for example. Now, there are plenty of examples of such surface active additives. What I am going to do in this next few minutes is give examples of or give generic examples of these additives, how they work, and give few examples of such additives. Now, let us first talk about polymer additives which work in polymer air interface. First, let us talk about additives antifog or antifogging agents. Now, if you think about a polymer wrap, a transparent polymer wrap which are used in a grocery stores, which are used for wrapping these fruits or food materials, and they are kept in a refrigerator and a freezer. Now, if in normal situation, what will happen? The water droplet will condense in that film and it will hinder your visibility, somebody else's visibility through that film because of fog formation, and customer will not able to look at the food material which is inside the wrapper. So, he or she may not buy that material. So, antifogging agents, basically a surface active agent which migrate to this polymer surface, and being hydrophilic in nature, it makes the polymer surface quite hydrophilic, and in a hydrophilic surface the water droplets cannot condense into beads. When they come in, the water vapor come in contact with this surface, they actually form a thin film of water which does not interfere with the light such a way that it basically gives any reduction in the visibility through this plastic material, or it does not decrease the transparency of this plastic material. Similar type of additives is antistat additive or antistatic additive, where additives which migrate to the surface and being water absorbing, it can absorb water from the atmosphere and form a layer of water molecules which form pathways for dissipating the static charges. So, if there are antistatic additives were not used, during the normal usage of the plastic material, the static charge can generate on the surface, which might give lot of hazard to the user. But if antistatic additives, surface active antistatic additives are used, then what happened, the surface active agents migrate to the surface and they absorb water, which form channels through which the static charge can dissipated. So, there is no formation of static charge. Easy clean or self cleaning type additives, which are basically very hydrophobic additives, which on migrating to the surface make the polymer surface very hydrophobic, such extent that when water droplet condense on it, it cannot hold on to the surface, it basically rolls off, because the contact angle between the water and the polymeric surface is very high. So, it basically rolls off, and during this rolling off process it can take away the dirt or the impurities which are present in the surface. So, basically this type of additives make the surface self cleaning. So, or easy cleaning, it is the cleaning of the surface is done easily. Next set of additives are basically used to make the polymer surface useful for biological applications. There are lots of applications where polymers or parts made of polymers are used in biological application. In those cases, the polymer surface comes in contact with biological fluid. Now, the surface of the polymer should be such that it should not interfere the normal biological processes, or it should not basically introduce or start the coagulation process in the biological fluids. For example, when a patient goes through a open heart surgery, the blood of the patient's body is taken out, and by help of external machine called oxygenator, which act basically as lungs and heart. So, it basically purify the blood and also pump into the body. So, this oxygenator is mostly made up of polymeric materials, and the membranes by which this purification is done is also made up of polymeric material. Now, there are so many other examples I can give where polymers are used for medical applications, where they are in contact with the biological fluids, maybe blood or serum or tissues and so on. So, the polymers must be biocompatible and hemocompatible if it is contact with real blood, antithrombogenic, because it should not start the coagulation process. Now, if we look at the steps or processes, what happened when a polymeric surface or any, for the matter of fact, any other external surface come in contact with biological fluid. The first step, what happened, proteins present in the biofluid, they get absorbed on the external surface, and subsequently there are lots of other steps which happens following that absorption process. Now, if we can make the polymer surface such that this absorption of protein can be prevented or minimized, then we can make this polymer surface hemocompatible or antithrombogetic, whatever we call that, or antifouling to protein, whatever name we can give. And that is done typically by using making the polymer very hydrophilic, or grafting or modifying the surface using surface active additives surface active additives make the surface rich with hydrophilic polymer, so that the incoming proteins is prevented from absorbing on the surface sterically. And one of the examples of the polymer used for surface modification is polyethylene glycol very often. So, these are some examples where surface active additives are used for medical applications, modifying polymer surfaces that are utilized for medical applications. Another example is antimicrobial, where basically there are some devices which are used by many people, like a computer mouse what I am using, it may have been used by somebody else. So, if this is this mouse is made up of the surface is antimicrobial additives, made up of antimicrobial additives, then it prevents formation of microbes on the surface of the polymers, and that actually prevent spreading of microbes among people. And typically surface active agents are used for this purpose. There are other surface active agents are used basically to improve the mechanical property of polymer surfaces, like scratch resistance, improved wear performance, and so on. And then some other specific examples like anti-glare, anti-piracy. These are some examples where surface active agents are used. Now, to be successful as a surface active additives, the additives must have some attributes. For example, it must be partially compatible. If it is completely compatible with the polymer matrix, then it will be soluble in the polymer matrix, so it will not come out to the surface. And if it is completely incompatible, then it will bloom out of the surface, so there is nothing will remain. So, the additives in this case must be partially compatible, so that it migrate to the surface, but be in the polymer matrix. Second, it should have low surface energy component, so that it migrates during processing technique or molding processes. It migrates to the surface to minimize the surface energy. At least part of the surface part of the additives must have a low surface energy component. It must be thermally stable, so that it can survive the processing condition, and it should be chemically unreactive to the base polymer it is being used. So, basically these are the attributes a surface active additives must have to be successful in any application. Some other application which work other type of surface, like polymer mold surfaces, to improve the mold release property of the mold of the polymer material. Mold release are added. Mold release basically the polymeric surface active agents which have long hydrophobic tail, and because of presence of this low surface energy long hydrophobic tail, they migrate to the surface, and as a result they form a lubricating layer on the molds on the polymer surface. So, they can be easily released from the polymer mold. The other examples of surface active agents which are used for dispersing a solid filler in polymer matrices, so that if you use external fillers, particulate fillers to disperse them well in a polymer matrices, some surface active agents are used which are basically covers or sit in the interface between the filler and the polymer matrices, and thus helps the dispersion of the particulate fillers. Compatibilizers, they are like block copolymer type surface active agents which go and occupy the interfaces between two polymer phases to reduce the interfacial energy between the two polymer phases and act as a compatibilizer. Some example or few example of surface active additives. Now, like these additives or the other additives we talked about, they could be small organic molecules or inorganic molecules, or they could be oligomeric or polymeric additives as well. For example, this PTFE polytetrafluoroethylene are added to the polymer to improve the wear resistant or coefficient of friction. Because of the low surface energy, it migrates to the surface during processing, and the coefficient of friction of these fluorinated polymers are very low. So, they form lubricating layer on the base polymer surface and improve the wear resistance. These are the examples of few mold release agents. As I said, they have a long tail, hydrophobic tail, and because of this they migrate to the surface and form a lubricating layer, and which helps release of the polymer article from the mold. Examples of improving hemocompatibility or biocompatibility of polymeric surface is like Tegomar, which is a block copolymer of polycaprolactone and PDMS. Because of presence of PDMS, it migrate to the surface, and because of hydrophilic nature of polycaprolactone, it basically form domains of hydrophilic and hydrophobic regions, which actually help in being the surface biocompatible or hemocompatible. Let us move to the next set of additives, which are fillers, which are mainly used to reinforce the polymer performance, mainly benefiting the mechanical properties of the base polymers. And many types of fillers, mainly inorganic, are added to polymers for different purposes, and some of them are listed here. And inorganic fillers, they themselves has high modulus. So, these by adding these inorganic fillers, at least it increases the modulus of the base polymer. And some of the newer fillers which are nowadays used in polymer matrices or polymer formulations are nano fillers, and when they are added, these nano fillers are added to the polymer formulations, the resulting formulations or resulting polymers are called nano composites. Some nano materials which are used as a filler are nanoparticles. They are particles having diameter between 1 nanometer to 100 nanometer range. It could be silica particle, titanium dioxide, and conducting particles, and so on. There are many examples of such nanoparticles. Nanowires or nanofibers, where it is basically whisker of filaments with diameters in the range of 100 to 10 to 100 nanometer, having high aspect ratio. Nanotubes, especially carbon nanotubes, because of their very highly high potential, this single wall carbon nanotube or multi wall carbon nanotubes are nowadays used for different polymeric nanocomposites. Nanoclays, they are layer 2 dimensional structure and having thickness in nano dimension. They are also used for in nanocomposites, and other fullerene, spherical fullerenes and others also used as a nanofillers. Now, what it does to the base polymer, the nanofillers actually improve the some of the properties of the base polymers like strength, modulus, toughness, heat distortion temperature, UV resistance, barrier properties. We gave the example of nano clay during the discussion of barrier properties. It basically increases the tortuosity or increases the path to be covered by a gas to come out of the polymer thickness. It also increases thermal and electrical conductivity if they are used in proper amount and their dispersion is proper. Obviously, they also bring some challenges. For example, with these inorganic fillers, the transparency of the base polymers is basically come down, and that is because, as we discussed earlier, difference in the refractive index between these fillers and the polymer matrix, and if the size is large, then it can cause lot of scattering. The ductility also come downs along with increasing in the modulus by these nanofillers, and thermal stability may be sometimes also questionable, because this might bring some impurities along with these fillers. So, that might cause some questions about the thermal stability of this polymer, especially at the high temperature or in during the processing condition. One example is shown here. This is a monomonturide clays, which is very commonly used nano clay, and they having layered two-dimensional structure. And so, ideally, to get the best property from the clay as a filler, they has to be dispersed quite well. So, their layer has to be dismantled and dispersed like what is shown here, and we call this as exfoliated nanocomposite. And that happens if there is the very good interaction between the polymer matrices and the surface of this clay. There could be intermediate scenario between these two, where the layers are separated to some extent with the polymer chains in between, and we call this as a intercalated nanocomposite. Obviously, to improve property, this type of exfoliated nanocomposite with nanoclays are always preferred. So, with use of this nanoclay, the base polymer, there is improvement in modulus, tensile and barrier and fire retardant property, but obviously with this the transparency comes down and ductility of the matrix comes down. Okay, with this, we basically come to our discussion on polymer additives, and there are other additives can be discussed, but due to lack of time we cannot discuss the entire list of additives used for polymeric material. What I did discuss the important additives which are very commonly used in polymer industries. Now, briefly talk about polymer blends. Polymer blends is basically mixture of more than one homopolymers or copolymers. Now, to bring why do you require to bring or mix two polymers? Sometimes what happen, one polymer is not sufficient enough to meet all the stringent requirement of properties for a product. So, sometimes by using another polymer mixed with another polymer, the properties is met. So, we discuss, let us define few terms related to polymer blends. Polymer blends, as we know, is a mixture of at least two polymers or copolymers, and miscible polymer blend is a mixture of polymers which are homogeneous at molecular level. Remember, we talked about while discussing the TG, glass transition temperature, we discussed that this miscible polymer blend has a single TG, basically they are molecularly soluble with each other. So, they are homogeneous at molecular level and Gibbs energy of mixing for this type of blends is negative. So, they are thermodynamically miscible. Immiscible polymer blends where the individual polymer components are phase separated. So, they are thermodynamically immiscible, the delta G mixing is positive. Now, for a application point of view, immiscible polymer blend is not useful, because then what happens during processing, they delaminate from each other, because they are not miscible at all, they come out and you have a delamination problem, one layer comes out. Whereas, miscible polymer blend is not also desirable from in practical point of view, because if it is a miscible, then you get a property which is a average of those two homopolymers. So, you do not get best of the two polymers which are mixed for making the blends. So, it is always preferred to make blends which are partially miscible or compatible, we say, we use the term compatible, where the individual phases of those polymers are maintained, but the interfaces are somewhat compatibilized using compatibilizer like block copolymers made up of two different homopolymers. So, basically interface between those two phases are stitched, so that they are not immiscible to that extent that they delaminate, but they are not also miscible. So, you can get the best properties of those two polymers as well. So, we talked about compatible polymer blend and polymer alloys are basically immiscible polymer blends with modified interface. Now, if we look at the thermodynamics of mixing, we discussed that Florey-Huggins theory or polymer solubility, and where we have seen that entropy of mixing is given by Kt N1 ln phi 1 N2 ln phi 2. Remember, we did this expression, and this is for polymer solution, where N1 is the number of molecules of component 1, N2 is for component 2, and phi 1 and phi 2 are the volume fraction of first component and second component. Now, if we increase the molecular weight, of a polymer, what happens? This number of molecules comes down. So, the entropy of mixing contributes less and less to the mixing Gibbs free energy. So, if you have very high molecular weight, then the entropy of mixing is basically negligible. So, the high molecular weights blends or the polymer mixing is not entropy driven. So, it is basically the enthalpy of mixing what determines whether two polymers will be miscible or not. So, if entropy of mixing enthalpy of mixing is negative enough, then the polymers will make miscible blend, and if they are even 0, then also because of slight entropy contribution, they may form miscible polymer blend, but if this is positive, then obviously this will form immiscible polymer blend. Now, to have a negative value of enthalpy of mixing, there should be some specific interaction between the polymers, and those specific interaction are shown here. Some of them are these hydrogen bonding, ionic interactions, or electron donor acceptor complex type. So, basically what we need to know that because of the high molecular weight of polymers, the entropy of mixing is not contributing significantly to the Gibbs energy mixing. So, it is basically the enthalpy of mixing which determines whether a polymer blend will form miscible blend or not. This will be clear with a few examples. Let us talk about two molecules, decane and substitute methyl substitute decane, like 2, 4, 6, 8, 10 pentamethyl decanes. Now, if you mix these two molecules, they will mix it easily, no problem. Okay. But similar polymers like polyethylene, if you increase this chain long enough, it will make polyethylene, and if you increase the chain both sides long enough, it will make polypropylene, but they do not mix, they do not make miscible blend. Because there is no specific interaction between these two polymer, their enthalpy of mixing is not negative, and because they are of high molecular weight, their entropy of mixing is not contributing enough to the Gibbs energy of mixing. So, they form immiscible blends. Another example we can talk about, say, bisphenol A polycarbonate and polymethyl methacrylate. If the length or the molecular weight of polymethyl methacrylate is high, then they do not form miscible blend, whereas these two form miscible blend as long as the molecular weight of PMA is small, like oleomer. So, as we increase the molecular weight, the solubility or miscibility between two polymers come down, unless there is a specific interaction which makes the enthalpy of mixing negative, which happens here, like polyethylene oxide and polystyrene. Because of presence of aromatic rings, they can do pi string interaction between them, and because of this specific interaction, they form their enthalpy of mixing is negative, and as a result they form miscible blend. So, basically to form miscible blend, the molecular weight has to be low, and which is not a practical. So, for polymers which are having high molecular weight, mixing is always governed by enthalpy of mixing, and that has to become that negative. There must be a specific interaction like hydrogen bonding or pi stacking or ionic interaction between the two polymer molecules. Now, reason for blending, as we have just mentioned, this improvement for the base polymer, development broad property range of material, dilute of high cost engineering resins, and so on. So, let us we have discussed it enough earlier. We can blend by mechanical mixing. We can do solution mixing as well. We can dissolve those two polymer in a co-solvent and then form a film after that, and we can make a interpenetrating network by dissolving one polymer in another monomer and then polymerizing the monomer to make a polymer, which will make this as an interpenetrating network. Okay, let us come to the last very end of this course, and I just want to make few concluding remarks. Now, this is the polymer tree, where basically we make polymer from monomers, and monomer has to be characterized very well by all analytical technique to make sure that they are free of impurities, because if there are impurities in the monomer, they will be carried over to the polymers, and they are very detrimental for the use of the polymers. Once you make the polymer, we have we basically understood what are the different polymerization mechanism, like step growth mechanism, chain growth mechanism, and different specific technique, polymerization technique. We studied them in detail, and once the polymerization is formed, we have learned how to characterize those polymer, both from a chemical point of view, chemical characterization, and determine their molecular weight, their the solution behavior, their morphology, their thermal behavior, whether they are crystalline or amorphous. So, that all we discussed how to characterize a polymer completely. One, the polymer characterization is over, you go through the processing step and finally make the product. For the more processing step, we need to know few information about the polymers, and we have not studied the processing part in detail, but what I have done, I gave you the basic polymer processing technique which you must know to understand the polymer completely. And then we last few lectures we discussed the applications of polymer, in the sense that the different polymer properties and how they are evaluated, like mechanical properties, thermodynamics, and so on. So, we discussed in. So, as a polymer chemist, you be very efficient in first two step, monomer characterization, monomer synthesis, and then polymerization process and characterization of the polymers for synthesis. As a polymer chemist, you probably do not have to do the processing part or the characterization part, but then you must know the techniques by which the processing is done, or the techniques or different properties, and importantly the structure property relationship between the property and the chemical structure. Unless you do not know the structure property relationship between the property which will enable the polymer to be at the final application, you cannot design new polymers. Lastly, we just go back and look at the big picture, a bird's eye view of the polymers. Polymers are applied when they are made in a solution or in bulk. They are synthesized in solution polymerization. They can be synthesized in bulk like in melt condensation polymerization. Polymers are also can be procured, though very less quantity, from natural resources, and these polymers are formed from monomers by polymerization, different polymerization techniques. What are the source of these raw materials, monomers? Mainly they are from petroleum sources. So, current trend, one of the important trend or requirement for polymer chemist at present to find out natural sources, because petroleum sources will be over sooner or later. Not only that, petroleum sources, the polymers made up of petroleum sources actually causes lots of environmental problem like greenhouse gas emission and so on. So, as a polymer chemist, the current challenge is to make polymers which have good properties for application, to be able to find application, how they can be made from monomers which are sourced from natural sources. We talked about additives which will be added during compounding or processing, and we get either the intermediate products which are sold in market, or we can get the simple shaped final product like sheets, film, etc. And some of the some will take these resins in plates or granular form and then make the other additives to make the final part. Now, after making the polymer product, what is the fate of the polymer? This is again another very contemporary topic of polymer waste. Lots of governments are banning plastics bags, mainly because the waste it generates are not degradable, and so basically they create lots of environmental hazards. So, waste management of polymeric materials is a very important step, and like the one where polymers need to be synthesized or produced from natural sources. Again, this is another contemporary very important topic for a polymer researcher, that what happened after. So new researcher should focus on to make efficient waste management of the polymers which are used for different application. If they can be made biodegradable, that is fine. If they are not biodegradable, then if based whether they can be recyclable again to meaningful product, or if they are not biodegradable or recyclable, then how the waste can be managed. So, that is one of the very important questions for polymer chemists at this moment. And obviously, nowadays polymers are finding newer and newer applications. Polymers are not only applied for the commodity applications. The polymers are now getting or finding applications in very high end products, especially also in healthcare related products. So, with this I come to the conclusion of this course, and thank you for being with me with this course, and good luck to you, and I leave my email address in case you need to contact with me for any reason. Thank you.